So today we'll be talking about quantum quenches near criticality, which is a topic to which I devoted these 3 papers, the second of which has been written together with Jacopo Viti, who was in the conference last week. Okay, so let me start recalling what a quantum quench is. So we have some quantum system, isolated, extended system, which for time t less than 0 has an Hamiltonian h0. And the system is in the ground state of this Hamiltonian. So it is a stationary state. Then at t equals 0, one changes a coupling of this system and obtains a new Hamiltonian h. And then the system evolves according to this new Hamiltonian for positive times. So this operation of changing suddenly the coupling at t equals 0 is called the quench. So the question is, what is the time evolution of observables after the quench? Now, this problem has been studied quite extensively in the last decade or so, because it provides a prototype of so-called non-equilibrium quantum dynamics. And a special interest has been attracted by the one-dimensional case, mainly following some experiments with quantum gases, in which somehow a lack of relaxation was observed for some quantities, which somehow continued to oscillate in time rather than relaxing to some constant value. And it was proposed that this was due to underlying integrability of these quantum gases. So the problem has been studied a lot. On the other hand, it proved quite hard to be addressed theoretically. So the post-quench state was calculated exactly for the transfer field Ising chain, which corresponds to free fermions. But on the other hand, it proved extremely difficult to find exactly solvable cases in which the quasiparticles are interacting. So the question has been around of how to gain some general insight on this type of problem and on the role of integrability in particular, and more generally of interaction among the quasiparticles. So my suggestion has been to look at this problem near a quantum critical point. Meaning by this that both before and after the quench, the system is close to criticality in such a way that the correlation length is large, but finite. So we can take some continuum limit that will give us some massive quantum field theory description. There are some advantages of looking at the problem in this setting. So the first one is that one obtains a general formulation that can be applied to the different universality classes of quantum critical behavior. And moreover, in relation with integrability, in 1 plus 1 dimensional quantum field theory, we have a sharp notion of integrability in terms of factorization of scattering amplitudes. And so conclusions that we may obtain from field theory about integrability then can hold also on the lattice, because if you find that the problem is non-integrable in the continuum in some cases, then this means that it will be non-integrable also on the lattice, at least as long as the continuum limit of the lattice formulation exists. Okay, so let's see then this field theoretical formulation. So I consider a translation invariant one-dimensional system near criticality. So as I said, the pre-Quench Hamiltonian is H0. H is the post-Quench Hamiltonian, which is obtained adding this term, in which lambda is what I call the Quench parameter. So it's the parameter we switch on to perform the quench. And the conjugated operator psi is what I call the quench operator. Then in field theory, it's useful also to go to the description in terms of the action of the theory. So we start from the quantum critical point that I consider to be described by conformal field theory. And so I have for it this action ACFT. From this, we can write down the action of H0 corresponding to the pre-Quench Hamiltonian H0. So this is given by the conformal action, to which we add some operator little phi that brings the system away from criticality, so it gives a finite correlation length. And at this point, we can write the final total action for the theory in presence of the quench, adding to this H0 the quench term, which acts only for positive times. So this is a non-time translation invariant quantum field theory, and it is the quantum field theory we have to deal with. So the first question we can ask is about the integrability of such a problem. And we can start from recalling what we know at equilibrium, so without any quench. We know we have a sharp notion of integrability, in this case, in the particle description. So these particles or quasi-particles describe the collective modes near criticality. And so if we have a scattering process of 3 such particles, say, we know that if integrability is there, we can shift the trajectories of these particles and still have that the scattering amplitude for this 3-particle process and for this sequence of 2-particle collisions have to be the same. So this is the so-called factorization of scattering amplitudes in integrable field theory, which is the signature of integrability. Then we ask whether this type of factorization can hold in presence of the quench. So in a quench theory, so there is a pre-quench and a post-quench theory, and they talk to each other. And so this means that information has to pass from negative to positive times, and this will be carried by particles. So we need particles transmitted through t equals 0. That is the quench time. On the other hand, such a theory is also non-time translation invariant. So this means that at t equals 0, we can create or destroy particles. The simplest thing you can do is to create a pair with opposite momenta in such a way to preserve the total momentum, since the translation invariance in space is preserved by the quench. Now, if there is integrability, if we, again, we can shift the trajectories of the particles. So we have to require that these two configurations correspond to the same global amplitude. But here this is problematic because we have this bulk scattering here and here, which occur for different total energies. So if I call little s here the center of mass energy of this process, it will be different from the center of mass energy here S prime. So the only way to satisfy this constraint is to say that S, the scattering amplitude, and the bulk is a constant. And in massive theories, this means that we can only have free bosons, S equal plus 1. S small is this traditional notation for the center of mass energy here. Okay, actually the square of it. Mandelstam Weber. So the conclusion is very simple, is that the factorization and then integrability for the quantum field theory corresponding to a quench occur only if the quasi-particles do not interact. So this is a conclusion obtained in the continuum, but it will also apply on the lattice as long as the scaling limit from the lattice can be taken. And this explains why it has been so difficult to find spin chains in which this quench problem could be implemented exactly. So the only exception essentially has been this the XXZ chain starting from the null state at delta equal infinity, but delta equal infinity is a situation in which you cannot take the scaling limit, so it is not in contradiction with the field theoretical conclusion. Okay, so summarizing, near critical quenches are exactly solvable or integrable only if the particles do not interact, both before and after the quench. So this leaves room only for mass quench of free particles, which are Bogoliubov solvable. And this is the case of the well-known. Yeah. This mass quench for free particles in particular is the case of the quench in the transverse field Ising chain. The quench is a quench in the transverse field itself, which corresponds to change in the mass of the fermions. You can find by a Bogoliubov transformation essentially the post-quench state. Everything is quadratic. Okay. So the conclusion about integrability is quite negative, but the problem remains. So physically is interesting, and one would like anyway to understand what's going on in this problem. Okay. So it is clear that the only way to progress is to use perturbation theory at this point. So let's see this perturbation theory. Again, this is the theory we have to deal with. And the perturbation theory will be a perturbation theory in the quench parameter lambda, in such a way that the Ampertard theory is the equilibrium theory, the pre-quench one, H0, that is sufficiently under control. So my notation will be, I will use this notation for the vacuum and multi-particle states with momenta P1, 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 Pn in the pre-quench theory, in this theory H0, yeah, the Ampertard one. So by definition of the quench problem, the system is in the ground state 0 up to t equals 0. Then the quench drives it into a post-quench state that we can express in this way. This is called psi 0. A is action, and I'm using the action. Psi is the operator which I had. It was already in the Hamiltonian, yeah. You see? No, here I'm very general, very general. Hermitian. We have no reason to violate Hermiticism. Lambda is real, yeah. Everything is physical. So, I can obtain this post-quench state acting on the vacuum, which is the pre-quench state, with the scattering operator of the quantum field theory, which has the usual form of the scattering operator, with this peculiarity that the perturbation acts only for positive times. Okay. Then we can write down the result here to first order in lambda. It takes this form, where EP is just the energy of a particle with momentum P and mass capital M. And then you see that all the dynamical information is encoded in these matrix elements of the quench operator on these multiparticle states. These are called the form factors of the pre-quench theory H0. So, yeah. Yeah. Psi is the operator, is the piece that I add at t equals 0 to the pre-quench Hamiltonian to obtain the post-quench Hamiltonian. So at this point, it's very general. It just you can. No, in general, it doesn't commute. So I'm very general, as I said. I don't need to specify anything more at this stage. Okay, so I rewrite this result for this post-quench state, just to stress that, as a matter of fact, this is the only existing general formula for this post-quench state. So from it, in particular, we can see that the only case in which the post-quench state is made of pairs of particles. Yeah. Lambda is constant. No. I mean, yeah, this is instantaneous quench. Lambda is a constant. It does not. You see, the time dependence comes when you integrate over time for positive time. Okay? No, don't worry. The state, sorry. No, the time dependence will be in the observables. When I calculate the correlation functions, they will depend on time. But the state, I have a transition from a pre-quench state, which is the ground state, to the post-quench state, which is that one. Okay? Yes, essentially. Okay, so I was saying, having this formula, we can see in particular that the only case in which the post-quench state is made of pairs of particles with opposite momenta occurs when there is no interaction among the particles. Because in that case, we know that these matrix elements here will be non-zero only for n equal 2. And then you have this state due to the total conservation of momentum. So I stress this because the structure of the post-quench state with the pairs of particles, in absence of this formula, had been assumed extensively in the literature. Okay, but we see from the explicit calculation that it occurs only in a very specific case, no interaction. So as a matter of fact, this is the only analytic framework for quenches in presence of the interaction. So the main dynamical information is carried by these form factors. So if they are calculated in the pre-quench theory, so if the pre-quench theory is integrable, you know explicitly exactly all these matrix elements, and so everything is computable. Yes, all these states here are states in the pre-quench theory. So as I was saying, if the pre-quench, so the total problem in presence of interaction is not exactly solvable. We have to do perturbation theory. But if the pre-quench theory is integrable, we know exactly all these matrix elements which enter the perturbation theory. So everything is computable. And so I'm writing here the first order. Let me stress that this is, as you see, already something non-trivial, okay? Because generally we start, the pre-quench theory we start from will be already interacting, okay? It's some very non-trivial theory. And also the first order result will become exact if we perform a quench which is sufficiently small. And this is still non-trivial. Okay, so having the state, we can go to calculate observables. So in particular, the one-point functions, which are the expectation values of some operator, capital Phi, on the post-quench state, side 0. I will find convenient to consider actually the variation of this quantity with respect to the pre-quench value. So I call delta Phi this variation. Capital Phi is some operator that you want to calculate. For example, the order parameter of T. Again, I'm very general, so you use the previous expression for the side 0, and you obtain this first order expression for the variation of the one-point functions. You see, I'm adding this constant C phi, which is determined requiring continuity at t equals 0 of the one-point function. So this doesn't come for free in the scattering formalism. You have to impose this continuity condition at t equals 0, and then you get the explicit form of this C phi. So it's known. I don't go into the details of this. I just stress that it is known since it becomes also relevant when comparing with numerics, since it sets the offset of the time evolution. Okay, so I rewrite here this formula. And one particular interesting question we can ask is, what about the long time behavior of this quantity? Okay, this is a main question of the problem. So talking about long time behavior, we have to understand that there are two time scales. One is the inverse mass gap of the pre-quench theory. And then the other time scale is brought in by the quench, because the quench parameter lambda is dimensionful in general, so it will give a time scale t lambda expressed in this way in terms of the scaling dimension of the quench operator, this x psi. So clearly, working a finite order in perturbation theory, we cannot pretend to follow the time evolution beyond the perturbative time scale t lambda. So when we say perturbative long time regime, we mean this time window. Okay. X sub psi is given psi, there is its scaling dimension that normally is known exactly if well, when psi, so suppose we are in this model, a transverse field is in chain. So if I take psi to be the longitudinal magnetization, this x psi is 1/8. It's the usual story, okay? So this long time regime will be in this window, which means that intrinsically in the problem, since we cannot solve it exactly in presence of interaction, the time evolution beyond this time scale t lambda is inaccessible. Okay. On the other hand, it's important to stress that you see from here, this t lambda can be made arbitrarily large, making the quench sufficiently small. Is a relevant operator. That is irrelevant, that we don't want, okay? So I'm skipping some details. When this psi operator, we mean is a relevant operator in the renormalization group sense, which means that its scaling dimension is smaller than 2. So that's smaller than 2. So that's always true. This statement is true. Okay, so once we understand this point, which is important, we can ask about the computing this long-time behavior in this regime or this formula. You see everything here, the main structure is in these matrix elements. So the time dependence appears here. And for large times, small energies, and then small momenta dominate. So we need to know the low energy behavior of these matrix elements in order to understand what is the long time behavior. But we know that in 1 plus 1 dimension, quite generally, the low energy behavior is determined by a fermionic statistics that appears. And so we know that this product here will behave a small momentum in this way. So we can plug here and obtain this result for the long time evolution. See, phi is some constant. This one is a constant which it was coming here. So it is determined requiring that the one-point function is continuous at equals 0. Yeah, and sum 0 is the crucial ingredient of this result, because you see the result as an oscillating part times a damping prefactor. And the damping is ruled by this n0, which from the calculation is the smallest n, so in this sum is the smallest number of particles for which both these two form factors, for the quench operator and for the observable, are non-zero. Okay? And now the interesting thing is that to kill a form factor, you need some symmetry, otherwise it's non-zero. So what we are seeing here is that the main feature of the time evolution, long time evolution, this in particular this damping prefactor, is dictated by the symmetry. So you integer it comes from here, from 1 to infinity. So n0 is the leading contribution in this limit. So I rewrite here this long time formula. And you see in particular that if n0 takes its minimal possible value, which is 1, then the damping disappears. There is no damping. So you get undamped oscillations. Here I'm referring to the case for simplicity of notation in which there is just one species of particles. So. But in general, there will be several species that we can label with an index A. And then you will get not just one frequency of oscillation, but you have to sum over all particle species, so you get multiple frequencies. M sub A is the mass of species A. So you see, if there are no symmetries in your problem, this n0 will certainly be 1, and you get for sure these undamped oscillations. On the other hand, if you have some symmetry, this n0 can be larger than 1, and normally it will be 2, meaning that you get the damping with the power 3 alpha. One thing to be stressed is that if there is no interaction, you will never see these undamped oscillations, because in that case, n0 will be larger than 1. This is just because in a free case, the quench operator couples only to two particles. Okay, so this is why these undamped oscillations were never seen playing with the transverse field Ising chain. So they can only appear in presence of interaction, and we see that it's all interaction which matters. Integrability, on the other hand, plays no role whatsoever in the undamped oscillations. Okay, so this is the general situation. Now we can illustrate how this works in practice on some model. And of course, the easing case is, as usual, the best illustration. So this is something we did in detail. Easy. Yeah, look here. The definition is here. I do this shift to bring the critical point in the origin. Okay. Well, in that case, I can just say that you get this 3 over 2. So you can compare, and you will get this 3 over 2. I'm not referring specifically to do that, but you can. Sorry, I was here. Let me start from the equilibrium case, no quench, just to remind some notation, some main facts. So the Hamiltonian is this, where I allow for the presence in general of the longitudinal field in such a way to have some interaction among the particles. Then we know that we have this phase diagram, and where I make this shift of Hz, as I said, to bring the critical point in the origin. We can take the scaling limit of this Hamiltonian, and this is the quantum field theory that we get. And we know that this quantum field theory is integrable in 3 cases. Of course, in the paramagnetic ferromagnetic case, which are free fermions, but we know from some logic of that also this vertical axis here is integrable. And we also know how the spectrum, particle spectrum of this theory changes in this plane here. So starting from the paramagnetic phase, there is one particle up to, okay, everything is ruled by this eta. So up to some value eta 2, there is one particle, then there is a sector with 2 particles, then a sector with 3 particles, and so on and so forth. And the number of stable particles increases going to the ferromagnetic phases. And so this vertical axis here, where the theory is integrable, falls into the sector with 3 particles, but due to integrability, we know from some logic of that 8 particles are stable precisely on this line. As soon as you move out of the axis, the 5 heavier particles decay. Okay, so this was the equilibrium situation. Now, starting from that, we can talk about quenches. So as I said, it's convenient to start from integrable directions before the quench. So we have 3, this, and this. And for each one, we can perform the quench either in the transverse direction or in longitudinal direction. So we have 6 inequivalent quenches we can describe in the formalism I showed you in this model. And they are summarized in this table. So you see, for each one, you have this little phi. It tells you in which direction you go out of the quantum critical point just to have the pre-quench theory, to have the finite correlation length of the pre-quench theory. And then psi is the quench operator. It tells you in which direction you quench. So it's the direction of the arrow. And then for each observable here, you can apply the results I showed you, in particular for the 1-point function, where everything was ruled a long time by that number n0. Here, I will just consider the order parameter. So I focus on this observable longitudinal magnetization. And these are the values of n0 you get just from the symmetries of the problem. And in the last column, I have the number of frequencies of the oscillations, which are 1 if I start quench from the free fermions, or 8 if I quench from the zamologic of E8 theory. So we can look at these quenches in some more detail. So let me start from quenches 1 and 2. So these are the two cases in which no longitudinal field is involved. So there is no interaction among the particles. These are completely free fermions, and this is the case, which I said before is Bogoliubov solvable. So we have results already exact from the lattice for these cases. So this is a case we can use just to check that the perturbative formula work, okay? Comparing with the results from other sources. And here I'm showing you just the time evolution of the order parameter in this ferromagnetic case. This is for Quench 2, in which you see the, so here you have this n0 equal 2, so there is the damping of the oscillations with the power t to the minus 3/2. And also you can observe that the asymptotic relaxation value here is 1/8, which is something that we can predict exactly for a class of quench to which this particular one belongs. I mean, we can predict in general for a class of quenches that the relaxation value will be determined by the scaling dimension of the quench operator. And this is one example. So, as I said, we can compare this with results available from other sources for this free case. In particular, Essler and Schurig obtained a large time expansion for this order parameter. And if you take their formula, you specialize it to the case of small quench that I'm considering here, you find exactly this result. I don't know. This is how. It's German, yeah. Okay. So now let me move to quench number 3. This is the first in which we have interaction among the particles. So this is arguably the simplest quench with interacting quasi-particles. And so is the first case in which this theory I've been describing is the only source of analytic information. And now you see that n0 for the order parameter in this case is 1, so we expect undamped oscillations a long time, and this is the explicit formula that you get in this case. There is just one mass here, so one frequency. Exactly. So this is first order result in H sub x. So this formula has been checked numerically by these authors, and one can see that everything is perfectly confirmed: the amplitude, the frequency, and the offset of the oscillations. In particular, they have this figure where, well, there are several curves here because in general they do mixed quenches, not only in the longitudinal direction, but also in the transverse direction. So here the curve that is interesting for us is this one, M0 equal M, so no transverse quench. And this corresponds to the oscillations with the maximal amplitude here. And you see that these oscillations are undamped. You also see that the minima of these oscillations occur at 0, which is non-trivial a priori, but is predicted by the formula. So everything is confirmed, in particular the presence of these undamped oscillations, which can only occur in presence of interaction. So now let me go to these quenches 4 and 5, which are the ones in which one starts from this vertical axis here, where the theory is already strongly interacting before the quench. And again, here there are no symmetry left because the longitudinal field breaks the Z2 symmetry. So necessarily we have to find undamped oscillations. And they come with 8 frequencies associated to homologic of E8 spectrum. So these masses here are homologic of spectrum. And these one-particle form factors are also exactly known because the pre-quench theory is integrable. Okay. So we know completely this formula. And also this formula has been checked very recently, actually, in this paper. And so this is the result always for the order parameter for quench 4. You see the points are the numerical data, and the curve is this formula. And you see that the agreement is complete. Similarly for quench 5, they have this figure. So here, again, the points are the data, but they have 2 curves here, so I have to explain maybe. So there is one curve which doesn't perfectly match the data. And this is because of this constant here. So it's a matter of offset, as you see. Remember that this constant here was expressed as a series. Now, for this quench, we are able to resum this series. It is related to the scaling dimension of the operator, so they could directly use the resummation and no problem. Here, instead, they first try to, the resummation of the series is not known, so they truncated the series to the first few terms, and this is not yet sufficient, so there is some small deviation in the offset. But if you shift the curve corresponding to have a total resummation for this number, you see that the agreement is complete. Then just a few words about quench 6 here. So in quench 6, again, you expect from the perturbation theory a damping with power 3/2 and 1 frequency. And this is certainly what you should see if you work for in the perturbative regime Hx small enough. On the other hand, there are no data in this regime. The only data available are for larger values of Hx. But then, in this regime of larger values of Hx, you have confinement prevailing. Because remember that here, when you switch on the magnetic longitudinal field, you have a confinement of the kinks of the ferromagnetic phase. So this is a stronger effect that produces this type of oscillations, which cannot be described by the first order calculation. But the first order calculation has to hold for Hx small enough. Okay, so this is to show that one-point functions are completely under control. One can also, in this formalism, look for 2-point functions, which have been studied a lot also in relation to this phenomenon that went under the name of the light cone spreading of correlations. So let me remind you what this is. So in some analytic calculations, one observed that the correlations between 2 points separated by distance r, develop only after a time proportional to r. Okay, there are no correlations before this time tr. And this was explained in 2006 by Calabrese and Cardi heuristically in this way. So they said the quench produces pairs of particles with opposite momenta. And they assume that these particles travel classically and without scattering, with the maximal velocity Vmax. This is, in general, you could also apply this argument on the lattice before taking the scaling limit, and then yeah. Yeah. Derivative of energy with respect to momentum. This is derivative of energy with respect to the momentum, maximal value. Standard. So if they travel classically and without scattering with maximal velocity Vmax, then you can say that the 2 points get correlated only after they are reached for the first time by particles emitted at the same point. And this happens after this time, which agrees with the available analytic calculation. So this was the heuristic explanation. R small is the distance between 2 points. Okay. So you have 2 points spaced at the same time, and you ask when they start to be correlated. How much time after the quench they start to be correlated. Okay. And the answer, they found this heuristic explanation. Okay. But you see that since this heuristic, it contains several assumptions that are not really intuitive. First of all, this form of the post-quench state in terms of pairs of particles that we saw is not true if you have interaction. And also, normally this is a quantum problem. The particles do not travel classically, and also they will scatter if there is interaction. So somehow this has been a bit mysterious, the effectiveness of this formula. And also generated, since then, it didn't really change the picture. It generated a belief that this light cone effect should somehow relate it to this pair structure of the post-quench state and to some form of non-interaction or at least integrability. So, and even experiments where this light cone was observed somehow were performed in this perspective of this picture. Okay, so it is interesting to look to this problem from a fundamental point of view and see what one can say. So this is what I've done in this recent paper. So first of all, we have seen that the form of the post-quench state is not made of pairs. Is already over? How many minutes? Okay, so I will be very short then. I will not go into the details of this. So you know the form of the post-quench state. This is the general form. The only constraint is this conservation of momentum. The total momentum has to be 0. Then you can plug this expression in this two-point correlation function, and you expand it over particle states. So you get 3 sets: one from side 0 here, one from here, and one intermediate set. And then you can analyze this result to look for, in which case, for large separation, so this x is the separation between the 2 points, when for large separations, the integrals here will not be suppressed. And this is obtained when there is some stationarity condition which is satisfied. Then you can show that this stationary condition, it can only be satisfied when the so-called disconnected pieces of these matrix elements enter in the game. So these are precisely the contributions that matter for this effect. And once you study these contributions, you find that the stationary condition is satisfied only when the time is larger than the distance over 2. And this is a situation in which the maximal velocity is 1 in my units. So this reproduces the light cone, but without any assumption on the quantum state or on the interaction. So I conclude just summarizing. We have the theory of quantum quenches in presence of interaction near criticality. This is necessarily perturbative since the interaction is not compatible with factorization. There is a time scale T lambda beyond which time evolution cannot be determined in principle. So this is intrinsic limitation of the physical problem. The long time behavior of one-point functions has been determined in general, and it exhibits undamped oscillations. They require interaction, but are in no way related to integrability. And there is perfect agreement with numerical data. And last, the light cone spread correlations has been derived from first principles. It requires no assumption on the quantum state or on the interaction. Thank you very much.